regarding the calculation, it's not too complicated. Actually, the result is very easy even to remember. You don't have to calculate. Actually, you can just remember those numbers. And actually, for several typical AC to DC converters, thyristor AC to DC converters, we require that you remember those results for the average output voltage. Let's see, for three-phase bridge, average output voltage should be equal to 2.34 U2 cosine alpha. And three-phase half wave, it is also easy to remember. That's the half of this 2.34. That should be 1.17 U2 cosine alpha. And there's another one I require you to remember. That's single phase bridge. Does anyone remember that? 0.9, right. Those are the results that you probably will be very often using in the future. Okay. Of course, when for the reducer load, there's a special case for reducer load. When the output voltage is discontinuous, then it should not be this result anymore. It has a separate result by this equation. Okay. And then you can also calculate the average output current, transformer current. Okay, those are all. This one is average value, but this one, if you talk about the AC current, we always look at the effective value. And then you can also figure out for the thyristor what is the maximum voltage it will see, and what is the effective value of the current flowing through thyristors. In general, this is the same. In this case, same as three-phase half-wave rectifier. You can find out why after the class. And for EMF load, EMF, electromotive force, that means in the DC side you have a DC source, voltage source in the DC side. If we also consider when the load inductor is large enough, then this is also the same situation, almost the same as the inductive load. Okay? Except the average output current, when you calculate the average output current, you should minus the output voltage should be minusing the EMF, the counter EMF in the DC side. All right, that's all for the three-phase AC to DC power converters. And then in the following part, I would like to discuss with you another issue, actually. We didn't notice before. This issue is, let's come back to the current waveform. Let's see over here. Okay. This is the inductive load. Inductive load for three-phase bridge rectifier circuit. We particularly, if you look at the current flowing through thyristor VT1, we have the current waveform drawing here. When VT1 is conducting, this current ID, load current ID, will be flowing through VT1, and during this interval, for the first 60 degrees, it is flowing through VT1 and 6. And for the next 60 degrees, it will be flowing through VT1 and VT2. But for both these 60 degrees and the next 60 degrees, for this 120 degrees, for the upper group, it is always VT1 conducting. Therefore, the current flowing through VT1 will always equal to ID, the load current. But if you look at this detailed waveform here, you see this load current, this thyristor current, before this point is 0, no current flowing through VT1. And after this point, there is an instant change. The current flowing through thyristor will be instantly changing from 0 to ID. This is the DC side load current. And at this instant here, before this point, this thyristor current is equal to ID, and after this point, this is suddenly, there's instant change, this current changing from ID to 0. This, in practical case, do you think what might be the problem in the practical case? What do you think might be the problem of those instant change of currents? What? Okay, that's, if you look at this, if you see this instant change in the current as an electrical engineer, you should always remind yourself this is a large dIdt. At these 2 points here, the current changing, and this point here, dIdt is almost approaching infinite, right? And when you have approaching infinite dIdt, we know if you have certain inductance along the current flowing parts, that would generate what? Voltage across the inductor, across that inductance, is equal to L dIdt. So when this is approaching infinite, then this voltage will be approaching infinite. Okay? That's the practical case. So in the practical world, if you have this instant change of current, there must be generating an infinite large voltage, and that's not good. Or in another way of thinking is that in the practical world, this voltage cannot be infinite large. So this voltage is always, there's always a limit on this voltage. Okay? So when you have an inductor here in the circuit, in the current flowing parts, this is a certain value, and you have a certain inductance. Then that means what? That means this dIdt cannot be infinite large. It is always under a certain limit. Or I would say this current changing cannot be instant. This changing process cannot be instant change. There is always a process as long as you have certain inductance. When you have certain inductance, this current changing cannot be happening instantly. That's the practical case. Now, so these are always, this instant change is ideal case. So as long as in the circuit you have some inductance, this current changing cannot be instant changing. Now let's look at this circuit here. IA current, that current IA should be equal to, during this during this time interval here, it should be equal to IVT1. Let me probably use another picture, it's more clear. Let's come back to the three-phase half wave. Okay, over here. For three-phase half wave, this is the current flowing through phase A, and phase A current must be equal to the same as the current flowing through VT1. So for phase A current, it would be this waveform, and the VT1 current also this waveform. Okay? Then in this picture here, you would say, in the practical case, there's always a certain inductance here. Because you have a transformer. Ideally, transformer has no leakage inductance. Leakage inductance. But in practical case, there's always some certain leakage inductance for transformer. And therefore, the equivalent circuit here would be not just a transformer, but also a leakage inductance in series with the secondary winding. Secondary winding. Okay, there's always certain leakage inductance in series with that. And therefore, this current changing, this current IA or VT1, in practical case cannot be changing instantly. Because there's an inductance in series with that. That inductance will always prevent, will always counting the instant change. Okay? That's the issue we are going to talk about. When you consider the transformer leakage inductance, what will happen? What are the result of those leakage inductance or effect of those leakage inductance? So in this picture you can see we draw particularly not just transformer but also the leakage inductance here. In each winding you have this LB is used to represent the leakage inductance for each winding. So because of this inductance, leakage inductance, the current flowing through this inductance cannot be changing instantly. The changing would be gradually. There will be a process. So you can see this waveform showing here. The current, if we do not consider the leakage inductance at this point, when we trigger VT1, the current flowing through VT1 will be instantly changing from 0 to a certain level. That's equal to ID, okay? And the current previously conducting flowing through VT3 will be instantly changing from ID to 0 at this instant. But this is not the practical case. In the practical case, because you have inductance, leaking inductance there, the current IA changing from 0 to ID will take certain time. Okay, current IC changing from ID to 0 will also take certain time. So it takes certain time for that to happen. And the current will be changing gradually. Okay, so the statement here you can see, commutation between thyristors thus cannot happen instantly, but with a certain commutation process. Now let's look at this process. Let's take example here. During this interval here, when you trigger VT2, let's look at here. When you trigger VT2, you want VT2 to be conducting, and therefore VT1 turn off. So it must be the interval during here. Look at this period of time. Originally, when you trigger VT2 at this instant, VT2 will be conducting. The current flowing through VT2, and the current flowing through VT2 will be changing from 0 instantly to ID, and the previously conducting current IA flowing through VT1 will be instantly changed from ID to 0 at this instant. But now this won't happen instantly. There is a process. Now let's see in detail during this process what happens. So the circuit would be, okay, now you have 3-phase half-wave. Remember the way I'm drawing the 3-phase half-wave circuit. This is a common cathode, and therefore this side will be connecting to the load, and the other side of the load is connecting to the center point of the input voltage source. And therefore this, you have label here UA, UB, UC, VT1, VT2, VT3. Now let's see what happens when you trigger VT2. Okay. Previously, the current is flowing like this. I'm sorry, previously it is flowing through VT1. Before you trigger VT2, it is flowing through VT1. Now when you trigger VT2, you want the current be flowing through VT2 in this way. Okay. During this commutation process, that means current flowing through VT2, this current is changing from 0 to ID, increasing from 0 to ID, and the current flowing through VT1 is changing from ID, decrease to 0 during this process. That means during this process, both these two, VT1 and VT2, both these two are conducting. Both these two thyristors are conducting. Okay, therefore, you can probably draw the equivalent circuit in this case during this process. You have UA, UB, okay? Because both are conducting, therefore, sorry, did I miss this leakage inductance? Okay. Yes, I missed leakage inductance here. That's LB. So the equivalent circuit during that process would be because both these two are conducting, and I consider these two as short circuit, VT1, VT2 as short circuit. And therefore, you have this load current here. Because this is a constant current ID, I therefore consider this as a constant current source. That will be the equivalent circuit during this process. Okay? Then I assume between these 2 points, when you trigger VD2, and after this commutation is over at this point, between these 2 points, this is the equivalent circuit. And if I label this current flowing, because this is a constant current source, therefore the current flowing through, I can consider there's only one current, which is called IK, flowing, changing between these two, that's within this loop. This current will not change because this is a constant current. Therefore, I can write out the equation, write out the circuit equation along this loop based on the KVL, Kirchhoff's voltage law. That is, okay, UB, let's see, this is the voltage UB, this is UA, UB minus UA, this voltage should be the voltage across these two leakage inductance. And that should be these two leakage inductance, that's 2LB, and then dIK dt. So that's the equation during this commutation process. Okay, and then I have the initial condition for this equation. Initial condition is that in this inductor, for this leakage inductor LB, in phase B, the initial condition is that this actual current flowing through LB, let's say I'm using IB, and this one is IA. The initial condition IB at 0 when we start to look at this process, that's 0. Initially, when this commutation begins, this current is 0. And the initial condition for IA, that current, in phase A current, the initial condition at this instant, IA, that's ID. Okay, those are the initial conditions. Okay. You have initial conditions, you have this differential equation. You can solve that differential equation because UB and UA is now known. Okay. UB and UA, that's UBA. Okay. During this process, UB and UA both are known. So you can solve this equation. Okay. There's a detailed illustration in the lecture notes. You solve this equation. You can get exactly how, you can get exactly this IK, how this is changing. You have a representation showing this current IK, how this current IK is changing. You can get the equation. So you exactly know how this current IA is changing, IB is changing. Because IA should be equal to ID, the initial current minus IK. IB will be exactly equal to this IK current. Okay. You can have analytical expression of those currents. Okay. But those are not what we really care about. What we really care about is that we want to know during this process, during this commutation process, how much is the voltage between, how much the load voltage is. The load voltage between these 2 points. Okay? We want to know when this commutation happens. We want to know the actual load voltage between this point and this point. How much is that? Okay? That is actually very simple. Okay? You have always this voltage UD here. This voltage. Okay. You can always write out this equation here. UD should be this voltage UD should be equal to UA plus the voltage across this leakage inductance. That would be UA plus LB dIK dt. Okay. And it should also be equal to this voltage UB. Is it in a reverse way? If UK, let's see, I'm sorry, that's good. That's correct. Because IK is flowing in this direction, so LB dIK dt would be in this direction. Therefore, UA plus this leakage inductance voltage, that should be UD. Okay. Then for UB, because IK is flowing this way, so the inductance current should be in this direction. So it should be UB minus LB dIK dt equal to UD. So you have this equation and this equation. Let me write it down here. UD is equal to UA plus LB dIK dt. And UD is also equal to UB minus LB dIK dt. Okay? And then you add up these two, equation 1, 2, you add up together, that will give you 2UD equal to UA plus UB. That means UD during this commutation process is actually equal to half of UA plus UB. That means what? That means during this process, the load voltage is equal to the average value of UA and UB. Okay? That's the average value of UA and UB. So if you look at this picture waveform here, during this process, if we do not consider this leakage inductance, this voltage will be changing from UA to UB instantly. But the actual case is that when you have leakage inductance there, the voltage between this point and this point will not be either not be UA nor UB. It should be the average value. It should be this line here, average of UA and UB. Okay? So the actual output voltage will be that waveform. So yeah, if I'm using this, it should be the load voltage at this point changing to the average value of UA and UB, and then after the commutation is over, it changed to UB. It would be something like this. So if this up voltage is changing to this, then what is the actual effect? Originally, we expect that the up voltage would be after this point changing to UB directly. But now it's not UB, it is half of UA plus UB. That means we lose, in up voltage, we lose part of the positive voltage in output. This shaded part. This shaded part is the part we lose in the output voltage. And then if you calculate the average output voltage value, if you calculate the average UD, in each, let's say this is, in each cycle here, you actually are losing 3 this shaded area. That means the average value of the output voltage will be smaller than ideal case. And then we can calculate exactly how much average output voltage you lose. You calculate that. Okay? There's a calculation in the textbook, in the lecture notes. We found out that for three-phase half-wave, rectifier circuit, this is the voltage you actually lose. You lose the average voltage by this value. It will be equal to 3 over 2 pi XP ID. XP is the reactance. XP is the reactance of the liquid inductance, so therefore it should be equal to omega LB. That means 2 pi F LB. F is the line frequency, 50 hertz or 60 hertz. Okay, that's the reactance. I'm not sure whether I tell you this word before, reactance. Actance. That's the reactance of this liquid inductance. So the reduction of the average output voltage is equal to this equation. And if you look at this equation, if I consider, you can see XP is a constant. You can see, look at this equation, the average output voltage reduction is proportional to ID, proportional to the average output current. So it looks like this effect is almost like you are actually having an extra voltage drop on the resistor, just like an average voltage drop on the resistor, because the voltage drop on the resistor is proportional to ID, proportional to current. Okay. You can also calculate through solving this differential equation. You can also calculate the commutation angle. That means for how much time this commutation process is lasting. Commutation angle. You can calculate that based on that equation. Okay? We usually use gamma to represent this commutation angle. And there is a discussion in the lecture notes about, or in the textbook, about the relationship of gamma, commutation angle. In the previous picture, actually, we have this gamma here. This is the commutation angle. Okay. There's a discussion about this commutation angle with related to other parameters. What affects this commutation angle? We know, of course, if this ID is larger, the DC average current ID is larger, then you take longer time. It takes longer time for this commutation to complete. So when ID is larger, gamma will be longer. Okay? When this is larger, then commutation angle will be larger. Okay? That's for sure, then we can understand it. Okay? Second, when the liquid inductance is larger, when you have larger liquid inductance, of course, it takes longer time. So gamma will also be larger. Okay? And then there's a discussion when alpha is smaller, when triggering delay angle alpha is smaller, this actually gamma will be larger, is it? I'm sorry, the reverse. When alpha is smaller, When alpha is smaller, gamma is longer. That's right. That's right. Why is that? Let's see. The first two are easy to understand, but what about the third one? When alpha is smaller, it takes longer for this commutation process to complete. Why is that? Can you figure out? You see, this is the commutation happening at this triggering the angle alpha. When alpha is smaller, or when alpha is larger, what's the difference does that make? You don't have any idea? Let me ask it in this way. What is the driving force? What is the driving force behind this commutation process? Why, when I trigger VT2, the current through VT2 will be gradually increasing, and the current flowing through VT1 will be gradually decreasing? Why is that? Because voltage, right? Voltage UB, when I trigger VT2, because UB is higher than UA, therefore when I trigger VT2, this voltage difference between UB and UA will generate this current here. So gradually, the current flowing through VT1 will be increasing, and this current, initially it's ID, but because this reverse current, the total current flowing through VT1 will be decreasing. So the driving force is what? Is the voltage difference between UB and UA. Because of this voltage, you generate this commutation process. And therefore, if you're clear about this, then you look at the voltage difference between UB and UA. Over here, let's talk about this interval. UB is that higher one, UA is this one. When alpha is smaller, that means what? The difference between UB and UA is smaller. And therefore, this driving force is smaller. And therefore, it takes longer time for this commutation to be completed. So that's why when alpha is smaller, gamma is longer. But this is true only when alpha is smaller than 90 degrees. Okay? When alpha is larger than 90 degrees, it's different. You see, after 90 degrees, over here. When alpha is larger than 90 degrees, then when alpha is larger, the difference between UB and UA will be smaller. That's the reverse. Okay? So that's the reason why when alpha is smaller than 90 degrees, okay, the difference between UB and UA will be smaller, therefore it takes longer time to complete the commutation process. So therefore gamma will be larger. When alpha is larger than 90 degrees, it is a reverse trend. Okay? There is a summary. Actually, we took a three-phase half-wave circuit as an example. But you can do this for all the different power converters, all different rectifier circuit. We have a table here, listing all different, for all different rectifier circuits. What is the total output voltage reduction caused by this leakage inductance? Okay. And how to calculate the commutation angle for each rectifiers. There's always there. Okay. Okay, there's this. We'll not get into details. You go through that after the class. Okay. And then you have a conclusion here. Commutation process actually provides additional working states of the circuit. That's how do we understand that? If we do not consider this leakage inductance, then the operation states, the switching states of this three-phase half-wave circuit will be only 3 states. Either VT1 conducting, or VT2 conducting, or VT3 conducting. Just these 3 possible states. But when you consider this leakage inductance, and when you consider this commutation process, then you have another 3. Not just these 3. You have another 3. The other 3 are 1 and 2 both are conducting. This is possible when these 2 are in commutation states. Okay? Or 2 and 3 are both conducting. That would be 2 and 3 both are conducting. That would be during this interval. And then, of course, 1 and 2 both are conducting. I'm sorry, the 2 and 3. Sorry, 3 and 1. 3 and 1, 1 and 2, 2 and 3. You increase, you add 3 other conducting states. Okay? The IDT of thyristor current is reduced. It's not going to be an instant change. You need a process. The average output voltage is reduced. And that reduction is proportional to ID, proportional to the DC load current. Okay? There's another discussion. There will be positive DUDT appearing, and there will be a notching in the AC side voltage. Those are a little more difficult for you to understand. We'll not also get into details in the class, but if you want to find out why there will be positive DUDT, that means the voltage will be, voltage changing will be positive, and then there will be a notching in the AC side voltage. Probably you need some time after the class to figure it out. And if you want to discuss that with me or with TAs, you are very welcome to discuss that. But we will not discuss in the class. Okay? Any questions? Any questions? If you don't have any question, then we'll move on to the next part. So today we're basically talking about three-phase bridge rectifier, how to analyze that, and how to calculate certain quantities for that circuit. We'll also talk about the influence of leakage inductance on the rectifier circuit. Any questions? If no, then we'll be moving on to next part. Actually, in the previous discussion, I guess you should have one question. Because when we talk about the different loads, different types of loads, we always mention when the load is a resistor, okay, or when the load is inductive. Inductive means you have both resistor and inductor. You must have a question, why didn't we talk about the other situation? Clearly, obviously, there's another, what is that? Capacitor. We never talk about when the load is a capacitor or capacitive. Here it is. We're going to talk about the capacitive load. Capacitive means you have at least one capacitor in the load. Okay? But this part we will not get into very detail. We just, and this, okay. And actually, the capacitive load is very widely used. In the future, you will see a lot of power converter, they are actually having this AC to DC rectifier circuit with capacitive load as the first stage. In the future discussion, you will see that. Let's see, this is a single-phase bridge rectifier. And we took a diode rectifier first. Okay, single-phase bridge. And the only difference between this one and the previous one we have already talked about is that the load is no longer just a resistor. The load is a capacitor in parallel with a resistor. And actually that capacitor really makes the analysis much more complicated. Because if it's just a resistor, the good thing is the load voltage and the currents will be having the same waveform. And that's easy for us to analyze. Or if the load is an inductive load, and when we consider the inductor is large enough, then we can always assume this load current is constant. That also makes things much easier. But when you have this capacitor here, that's more complicated. Why is that? Because when you have a capacitor here, then you always have a DC voltage. And this DC voltage is not constant. DC side, there's always a voltage, but this voltage is not constant. And therefore, it is hard to determine at what time those diodes are conducting. Before, when we don't have this capacitor here, if we do not consider this capacitor here, then it's always when this, let's see, when the input voltage is positive, then VD1, VD4 will be under positive voltage, and therefore those two will be conducting. Therefore, current will be flowing through VD1, load, and VD4 back to the source. And therefore, load voltage will be exactly equal to the AC voltage U2. Okay? When U2 is negative for this part, then it would be VD2 and VD3 are subjecting the positive voltage. Therefore, these two diodes will be conducting. So the current will be flowing through VD3, load, and coming back through VD2 and back to the input voltage source. And the load voltage will be equal to minus U2. This is minus U2. UD will be equal to minus U2. But in this case, this is very different because you have a DC voltage here and you do not know how much that DC voltage is. The only thing you know is that only when this input voltage is higher than this DC capacitor voltage, then there will be two diodes conducting. For example, for here, at this instant when U2 is higher than UD, VD1, VD4 will be conducting. Okay? So you don't know, or it is complicated to know at what time diodes will be conducting. This determines the complication of this capacitive load. Not just for single phase, but also for three phase. And not just for diode circuit, but also for thyristor circuit. So that's the complicated part. Okay, so you can see from the textbook, if you want to get into the detailed calculation, a detailed analysis, those are really complicated. But we'll be just going through the relatively simple qualitative analysis. We are no longer getting into details of that quantitative analysis in the future. Okay, so in next class, I'll be briefly go through this part. and will not get into details of calculation, detailed quantitative analysis. Okay?